right, let's get started. So this is the first of maybe 2 lectures, kind of using Hodge theory, for which probably won't get to it so much today, but I eventually want to kind of highlight sort of how omnimality enters into the story. Before any of that, though, I do want to say, because I posted it too late, that in the research seminar tomorrow, Chris will be speaking, and it's his last day here. You should definitely. And also, I apologize if you get an email about it later, because I tried to send an email this morning, but I think I failed or misunderstood the mail list.
No, I think I got one. Well, I got one, so that's.
Oh, did people get the email?
Yeah. Don't even edit it yesterday.
Oh, right. So I did figure it out. Okay, well, then I apologize for the redundancy.
While we're announcing, maybe you should say that your second talk won't be next week.
Oh, yeah, that's
but
a good.
But in 2 weeks.
That's a good point. So Hodge, basic Hodge theory 2 will not be next week on Wednesday. It'll be the following week on Wednesday.
Do we have something?
Yes, we do.
If you wanna, well, I guess.
It'll be posted, yeah.
Yes, it'll be posted. Timely, in a timely fashion. Okay, anyway, so let's start talking about Hodge theory. So what are the goals? I think I basically want to do 3 things. One, sort of what are Hodge structures and where and why do we care? Where do they come from? Where do they come from? 2, what are the sort of parameter spaces for Hodge structures? Or what are the moduli spaces? What are moduli spaces? And 3, how do they vary in families, especially sort of how do we get families of these objects from families of algebraic varieties? They vary families. Vary families. I guess it's a question. Yeah, so today I'll probably mostly do 1 and then I'll start to talk about 2. And really the sort of omnimality perspective will be most important in these 2 parts. Maybe I'll get to it a little bit today, but probably mostly next. Okay, also please interrupt with questions. So let's talk about 1. Okay, and let me do this in inverse order. Let me first tell you sort of why, if you're an algebraic geometer, sort of Hodge structures show up naturally. So let X inside a projective space be some smooth, complex projective variety. We don't have to be fancy. We can think of even just a hypersurface. So just something cut out by the 0 set of a single homogeneous polynomial. So 0 set of, I don't know, something that maybe looks like this. All of the monomials have the same degree V. Oh, my homogeneous coordinates are, say, x naught through x big N. So, now we can consider x, you know, as a complex manifold, and we can consider the underlying topological space, and we can compute the singular cohomology. So we can take singular cohomology, I'll say B for Betty, so the singular cohomology of X with Z coefficients. Singular cohomology. Okay, so this is, like I said, it's a topological invariant. So it completely doesn't see the algebraic structure or even sort of the structure as a complex manifold of X. And so in particular, if I like deform the coefficients of this polynomial, the underlying topological space doesn't change up to homeomorphism, and so this invariant doesn't change, okay? So a natural question is, can we enhance this invariant so that it actually depends on the holomorphic structure or even the algebraic structure? It doesn't depend. On the holomorphic structure. This is sad face. Can we enhance it? Okay, and there's a classical story that I want to tell that maybe you've seen before that tells you not only can we enhance it, but with kind of profound consequences. Okay, so let's consider an elliptic curve. So X to be an elliptic curve, which, for instance, concretely we can think of as the zero set, solution to some cubic. I'll write it like this: x cubed plus a x squared plus z cubed in P2. Turns out any one can be written like this. Sorry, it should be there. Sort of the algebraic geometer's picture is it's a cubic, so it looks like this. But the sort of topologist's picture is, as a complex manifold, it's just a genus one surface, it's a donut. And okay. We know from sort of complex analysis that as a complex manifold, E is always the complex plane modulo some lattice. Okay? And in fact, this lattice then gets canonically identified with the first homology. In fact, the fundamental group, because C is then the covering space. Okay, so we can talk about the singular cohomology. As I said, it's the first cohomology that's interesting. We can tensor this up with C. So we get this C vector space. So what is it? Well, the sort of first homology is generated by a loop here, like that, and this loop like this. Maybe it goes around that way. And then the cohomology is the sort of dual to that. So it's this space, the cohomology with C coefficients is are forms on the one cycle. So you associate to each one of these a complex number. Okay. Now there's another way to think about cohomology. We can think about it in terms of Durham cohomology. And let me be precise here. C infinity Durham cohomology. Complex coefficients. So what do I mean by that? I just mean that I take, smooth closed one forms modulo smooth exact forms. This is closed one forms modulo exact forms. And there's a natural map between them, in fact, an isomorphism. What is that map? Well, it's integration. Namely, I take the Durham cohomology class of some closed one form, say alpha, this is one form. And how do I associate to it a thing which can be evaluated on cycles? Well, I integrate. Right? So I send this to the form which sends a cycle gamma to the integral of alpha along gamma, and it only depends on the cohomology class of alpha. Okay, so with respect to this, this concrete basis that I wrote here, say alpha, beta, we might write alpha, and another way to say this is we just write alpha, sorry, I shouldn't say. We call this A and B. This is B. Oh, I already had an A and B. Okay, let me keep it alpha and beta. And let me change this to, I don't know, eta. Okay, so now we're writing the cohomology class of eta as, well, what does it evaluate on alpha? It's just the integral along alpha. So that's the coefficient of that basis vector. And the coefficient of the beta dual basis vector is just the integral along. Okay, so all of that is very sort of classical, and it doesn't involve the holomorphic structure at all, right? This is just the sort of this is just about smooth manifolds. So here's the key observation. Sort of this space of smooth Durham cohomology has a natural subspace sitting inside of it, namely the subspace of holomorphic one forms. Okay, and so that actually is going to see the holomorphic structure. Okay, in fact, for an elliptic curve, there is a unique up to scale holomorphic form. And it's the one which, you know, in the coordinate coming from upstairs, let's call the coordinate here z, is just dz. So that descends downstairs because it's a translation invariant. So this is just, dz, okay? And we can look how dz sits inside of this h1. Okay, so we get this line, multiples of dz, sitting inside, well, it sits inside here, but under this integration map, it gets embedded inside of here. See. And what are the coefficients in terms of this basis? Well, they're just the integrals of dz along this one and that one. And that gives me an embedding of lambda into c, right? Because these are the coordinates of this basis for the lattice. And we realize that E is then recoverable as C modulo this embedding of lambda. Okay, so what is the upshot? The upshot here is that, you know, this side of the board is only about smooth manifolds. So it doesn't care about the complex structure at all. But if we just remember this kind of shadow of the complex structure, namely which line inside of this two-dimensional complex vector space equipped with an integral lattice comes from the holomorphic one form, then actually we can completely recover the elliptic curve. So we've upgraded an invariant which doesn't depend at all on the complex structure to an invariant which is a complete invariant for the complex structure. Okay, so that's pretty good news. That's a hint that somehow we can get a lot of mileage out of understanding which Durham cohomology classes sort of come from holomorphic forms. Okay, so that story more or less generalizes to higher dimensions. And here's sort of the main example for where Hodge structures come from. So again, take X to be a smooth projective variety.
Sorry, but this line, the point is that lambda is recognized as the intersection of this line with the integer cohomology, right?
No, not the intersection. In fact, the intersection can't be anything because this, you know, this line does not intersect its conjugate. So it's more the coordinates, like choose a generator for this line and look at the coordinates in terms of the integral basis. And those two coordinates generate a lattice. And that's what gives you we identified this lattice with like the H lower one. So this map is literally the integration along DZ map. Right? But that is just taking the coefficients in an integral basis. Okay. Okay, so for X smooth projective, we can run the same story. We can still take Betty cohomology in any degree, complex coefficients, which is still just the integral thing. So this integral lattice tensored up with C. And we can also form K smooth Durham cohomology. X with C coefficients. There's still an isomorphism given by taking a class and taking the form that I get on K cycles by integrating. So what now is the analog here of looking at the line spanned by the holomorphic forms. Well, we're in higher degrees, so somehow there's more information. Namely, I can look at the subspace, I'll just for simplicity call it HPQ, where P plus Q sums decay. And these are all smooth Durham cohomology classes that can be represented by a form of type PQ. Okay, so what does that mean? This is classes representable representable by closed C infinity form alpha, sorry, eta, which is of type PQ. What does that mean? It means if I choose holomorphic coordinates, okay, so we're using a holomorphic structure. Let's say Z is dimension n. Then eta locally looks like, you know, some of stuff functions times, well, you take you take P many holomorphic DZs. This is I1 through DZ IP. Sorry, let me write this to be important. So let me write it bigger and down here. Okay, so locally, I'm just saying for it to be a PQ form, it means locally it looks like DZI1 wedge up through DZIP wedge DZ bar J1 through DZ bar JQ. Okay. So that's what I mean by this sort of, you know, if I write it locally in terms of the natural basis I get coming from these holomorphic coordinates, there's the ones that are sort of behave holomorphically in terms of Z. There's ones that behave anti-holomorphically. And if you have P many of these locally everywhere and Q many of these, then you're of type PQ. And you can look at those Durham cohomology classes that are representable by a closed form that's a pure type, P comma Q. Okay, that might be zero. Right? Nobody's guaranteeing that that is a non-zero space. It's in fact a hard condition to represent a Durham cohomology class in terms of a pure class somehow, because being closed becomes a much stronger condition if you're a pure type, because then the sort of the D of it is pure, but has two different types. So you're simultaneously requiring vanishing of both of those. But here's the important fact. For a smooth projective variety, in fact, not only are these non-zero, but every Durham cohomology class can be decomposed into pure type ones. So this is the Hodge decomposition. For X smooth projective, it's just a fact that the Durham cohomology of X is a direct sum.
Do you know like a complex manifold is as simple as possible or this is false?
Indeed, I was going to give that example and leave it as an exercise. It's the universal counterexample, the Hopf surface. I'll write about it. Yeah. Okay. So let's just see how this works for the elliptic curve. In the elliptic curve, we kind of already know the story. So going back to X is equal to E, what is this decomposition? Well, H1, I'll stop writing the subscript, E comma C is equal to multiples of the holomorphic one, that's the H10 part, plus C times DZ bar, right? So DZ bar is also invariant under translation and descends to an anti-holomorphic one form. And this is the 0,1 part, right? Because locally this is, you know, in terms of that decomposition I wrote down, pure of type 0,1. And that's the Hodge decomposition. Now notice that I remarked over there that being a pure type means being closed is a stronger condition. You can appreciate that here, because if you're a pure type, if you're a 1-0, if you're a smooth 1-0 form, being closed forces you to be holomorphic, right? So that's quite an upgrade over just being closed. Okay, great. So there's a slight warning. So we said X smooth projective. This question makes sense for any complex manifold, but as I said before, it's not true for any complex manifold, but it is true for any Kähler manifold. So actually the condition you need is you need X to be Kähler. If you don't know what that is, then it's fine because it's not really going to show up, but that's the precise condition that you need. And here's the non-example that you can think about. If you take X to be, so what is the Hopf surface? You take C squared minus 0, and you take a complex number T whose norm is, let's say, bigger than 1, and you mod out by the scaling action of T. So this gives you some complex surface, and this fails. So Hodge decomposition fails.
You say that's the precise condition you need. You mean that if you had the Hodge decomposition, it would be Kähler.
Sorry, say again?
When you say it's the precise condition you need, you mean the converse is?
No, I'm not saying that. No. I'm saying you need X to be Kähler for the proof to work, and somehow, it's not really clear how to prove it maybe in a more general class of things. Yeah, no, I mean, it might sporadically be true.
But
It can certainly be true for trivial reasons, yeah, but no, it's not the precise condition.
Ben, can I?
Yeah, sure.
Silly questions probably. So, what actually is the sizable content of the statement? Like, can you, for example, like, is it obvious that, like, if I take a form, then somehow this invariant PQ is universal for that form in all charts? Or...
Well, so if you take a random smooth form,
Yeah.
okay, you can write it locally in terms of pure type forms.
Yeah.
You can even write it globally in terms of PQ forms.
And PQ is sort of a constant as you vary over the manifold.
Yeah, I mean, sorry, for any form,
Yeah.
you can write it as a sum of, globally write it as a sum of things where each one is of constant type PQ. Just because these kind of form a basis, and if you move within a holomorphic chart, you don't change the type. But it is not true in general that you can decompose a cohomology class in terms of pure type. And I mean, the way classically the proof goes is you find harmonic representatives, then you use the Kähler condition to show that the pure decomposition of a harmonic representative is harmonic. And then once you know that harmonic representatives exist, you can then go back and prove that in fact the Durham cohomology classes that are of type PQ in the sense of being representable by a harmonic PQ form are just equal to all classes that can be represented by a pure type.
And then one even probably sillier question, like for the elliptic curve case, like you somehow it's enough to just consider constant multiples of dz. But
Yes.
like, a priori here, there's some function right, in the form. And I mean, of course, it's finite dimensional, but more.
Yes.
But so.
Well, these aren't even global things. These are like in terms of some local coordinates. So, I mean, yeah, it's unclear how to even compare with the elliptic curve in the sense that you don't have that global form.
Yeah.
Does that answer your question?
Yeah, I think so.
Yeah.
That's good.
Yeah.
As with Hopf, for example, you can divide C1 without 0 by T to the Z and you get elliptic curve. So here you get something which is not proper.
Well, so you get something, well, that's the kind of the point of this Hopf surface. It's an isotrivial family of elliptic curves over P1. Because each line is a C star modulo T. Because this is the diagonal line.
Huh?
It is proper. It's compact.
Yeah. This is an elliptic curve. This is a family of elliptic curves over P1.
Topologically, it's S3 cross S1, right?
Okay.
Well,
Any vector in C2 you can normalize back to norm, between 1 and 1/2.
yeah.
So it's compact.
Okay.
But maybe, I mean,
Yeah.
you can mod out by all scaling. That gives you a map to P1. And somehow the fibers, what are the fibers? They're C star modulo scaling by T, so that's an elliptic curve, right?
Plus one plus two, yeah, topologically.
Probably, because you're saying, well, yeah, maybe. Yeah, yes. Yeah, that's kind of, this is already a hint that there's something funny is going on, because this is a counterexample to many things, but this is like a trivial, this is a family of elliptic curves, all of which are isomorphic over P1, and therefore there can't be somehow any monodromy in this family, but yet it's not trivial. Okay, great. Okay, so now let's define what a Hodge structure is.
Sorry, so you didn't say in what sense the off surface is a counterexample to the.
Yeah, I said it in the sense that I left it as an exercise, but I can tell you the punchline to the exercise, which is that the H1 is one-dimensional. And that's like already a problem, because in fact, I was just about to write this decomposition, you know, HPQ is the conjugate of HQP, right?
Right, so if you drop the conjugacy conditions, there is a Hodge decomposition there.
Well, it's
not symmetric in the way you expect.
Well, I mean something precise. I'm by a Hodge decomposition, I mean this.
You're using the conjugacy condition as part of the definition.
Well, it's a consequence of the fact that by this being true, I mean, if you look at the subspace of classes of pure type, closed classes of pure type, then you get this decomposition. And with this definition, it is then a consequence that HPQ is HQP bar. So it's more than just saying that, having a decomposition like this with no meaning behind it is, of course, much weaker.
The point is, like, can you find closed forms of pure type? Like in this case, can you find a holomorphic one form which is closed? And you would need that to be true for the Hodge decomposition, at the very least. And that's not true.
Yeah, so what's true here is the H1 is one-dimensional, and the unique up to scale de Rham class cannot be written as a pure type form.
But just to when you say holomorphic form, you mean with holomorphic coefficients, or you just mean that it's only DZ, not DZ bar?
It's only dizzy.
Yeah,
it's only dizzy.
It's not a holomorphic form, right?
Well, it would have to be because you want to be closed, right? So you want D of
Okay. But I mean, just for the definition.
Yeah. If it's of like extremal type, like either K comma 0 or 0 comma K, being closed forces it to be as a holomorphic. Okay, great. So here is the definition. A weight K Hodge structure. I guess integral Hodge structure. We typically refer to it V, but V refers to a package of information. Is, so it's a Z lattice, VZ, a torsion-free, finally generated Z module. Okay, so that's this part. And a decomposition like that over C. So if I take VC, which I define to be just C tensor VZ, I give myself a decomposition into pieces BPQ, where P and Q sum to K, which satisfy a conjugate symmetry, such that BQ is equal to BQ. And that's the definition.
Ben, sorry.
Yeah.
So we could take the elliptic curve case and do like, look at the forms of type P0.
Yes.
And you look at all the periods.
Yes.
And then probably at some point you'll tell us like to what extent that determines X.
Sorry, in the elliptic curve case or in this general case? I could tell you that if you like. In general, it doesn't, so you need to include the data, sort of more than, so the kind of the holomorphic forms are just going to be kind of the first piece.
Yeah,
But you certainly need more information than that.
but is it easy to say when is that just
It's not easy to say exactly when it's true. There are many cases, and this I can give you an answer to, when the way the Hodge structure moves detects all like local deformations in your variety, but it's not going to be able to, often it's a subtle question. Like if you sort of take some global deformation, maybe it comes back to the same Hodge structure. But there are many cases in which it's kind of infinitesimal. This is when sort of infinitesimal Torelli holds or local Torelli. Other questions? I can, at the end, maybe I'll say some actually, the short answer is for all Calabi-Yau manifolds, it's just true. And then there's a bunch of other cases in which it's also true, but that's already kind of a big, okay, so here's just a remark. So I said Z Hodge structure, which was because I had a Z module. You can sort of have different coefficients here. I don't want to get too much into generality, but it is useful to be able to talk about Q Hodge structures. And also have weight K Q Hodge structures. Okay, so that was useful at least once. Okay, so let's come back to our main example. Again, this abstract definition is meant to kind of distill out from the examples we have, kind of all the data we get on the cohomology. That's sort of linear algebraic data, like the data that we can easily record. So there's another structure floating around. What is that? Well, again, let's take X. Again, might as well take it inside of PM. Let's say it's n dimensional. And let's actually consider the middle cohomology. Okay, so X as a real manifold is 2n dimensional. So the middle homology is Hn. Okay, so consider Hn of this. And the point I want to make is that there's a natural form given by cup product. Right, so there's a natural form Q alpha theta, which is given by, well, let me do it this way, because I'm actually going to care a little bit more about the Hermitian form you get by conjugating the second factor. This is just, you wedge them together and you integrate. Okay, so this is a natural thing you have. What properties does it satisfy? How does it play with this decomposition? Well, let's first understand the elliptic curve example. In the elliptic curve case, remember sort of H10 is multiples of dz and H01 is multiples of dz bar. So if I take this pairing applied to say dz, and I also plug it into the well, let me pair dz with dz bar. Remember, I'm kind of conjugating. So this is really just dz. This is the integral over E of dz wedge dz, which is 0. Okay. Somehow I have too many sort of I have, the dimension of E is only 1, but I'm trying to combine, too many holomorphic type forms, and that's something that holds generally. If alpha and beta are not of the same type, or if they're both pure but not of the same type, then this will automatically be 0. 0 if alpha is in sorry, let me just declare that alpha is a pure type PQ and beta is a pure type P prime Q prime. And I want to say this is 0 unless PQ is equal to P prime Q prime. Okay, so in other words, this Hodge decomposition for this Hermitian pairing is orthogonal. Okay, so that's the first thing we observe. Now what happens if I plug in the same thing into each slot? Let's again look at the elliptic curve case. If you plug in dz, what do we get? Okay, well now we're taking the integral of like dz wedge dz bar. Okay, well this is kind of a simple example, but the point here is that this, if I put an alpha here, right? So if I scale this, let's say A, then I'm also scaling, and I also scale this one, so I get an A bar there, I'll get a norm A squared. So the point is that this has a definite sign, like whatever the sign of this is not going to change it. And it turns out that, well, but you have to loosely interpret definite sign because it's imaginary valued, but it's a negative imaginary number. Okay? So there's some definiteness properties. And I'll be very vague here, some definiteness properties. Okay. So this brings me to a definition.
Is there an advantage to working with V Hodge structures instead of Q Hodge structure?
Well, in many cases, especially when they start varying in families, having the integral structure is important, yes. I mean, it's just a weaker notion. So many things are isomorphic as Q-Hodge structures that aren't. It's kind of like isogeny for abelian varieties. In fact, it reduces to that in the case of abelian varieties. So let B be a weight K Hodge structure, Z Hodge structure. A polarization is a -1 to the K symmetric form. Q, okay, so by that I mean when K is even, it's symmetric, and when K is odd, it's anti-symmetric. And it satisfies two properties, which are called the two Hodge-Riemann relations. This is Hodge-Riemann 1. The HPQ, the VPQ decomposition of V is orthogonal with respect to the Hermitian form you build out of this Q in the same way. So V equals the sum VPQ is orthogonal for this form. Okay, that's the first Hodge-Riemann relation. And what is the second one? It's a little sneaky, and this is related to why I was vague here. So the best way to say it is that, okay, so we now always know it's orthogonal, so it remains to say something about what it is on each piece. And what I want to say is that it's definite of alternating sign in each VPQ. Restricted to VPQ, definite of alternating sign. Okay, what does that mean? Well, for any individual VPQ that has meaning, if K is odd, this is imaginary valued, and if K is even, it's real valued. So in either case, it makes sense to talk about whether what sign it has, either, whether it's plus or minus, in here, or the minus of this, if it's imaginary valued, or in R bigger than 0 or less than 0. And whatever notion of sign you have for VPQ, it makes sense. It'll have, you'll be able to ask for the same notion of sign on V on the next one, and you just want it to be minus the sign. Okay, does that make sense? I'm using, this might be less clear than if I just wrote it out. But basically what I'm saying, let me just say it verbally. So if K is odd, then what you want is this times I times -1 to the P to be definite for each VPQ. And if this is even, you just want -1 to the K times this, because now it's real valued, is definite for each VPQ. Okay. actually leave that off. Perhaps not surprisingly, the with this definition is cooked up so that every cohomology group of a smooth projective variety has a polarization. So let me actually make a further definition. V is polarizable if it admits a polarization. Okay, that's not so surprising. And then the theorem well, I guess the example slash theorem, this is really just the main example continued. So just the main example. Is that for again, X smooth projective. Each cohomology group, HK Z, or HKZ has a functorial polarizable Z Hodge string. Okay, so let me just say a few words about this. So this is kind of the takeaway of this whole discussion. This is why the definitions in Hodge theory are made the way they're made, so that this theorem slash example is true. So because of the way I described it up here, namely that the Hodge decomposition is given by classes which are representable by a pure type form, it's clearly functorial, right? Because under a holomorphic map, a pure type form pulls back to a pure type form. Okay, this kind of avoids some of the annoyance of representing by harmonic forms, in which case pullback is not necessary, so it's a little bit funky. So that's why you have functoriality. What about this polarization? Well, I kind of defined something related to it in middle cohomology because I had cup product. So you might reasonably ask, what if you're not in middle cohomology? And you're a believer in linguistic determination, it's because of the fact that, the polarization of the Hodge structure comes from the polarization on the projective variety. So how do we make the form in general? So for HKX, let's say for X smaller than or equal to the dimension of X, how am I going to build a form? It's basically going to be that, except it might be the case that this wedge is not top degree. So I just supplement it with the natural form that's lying around, namely the Fubini study form on projective space. Okay, so let me say that in these words. So on Pn, so this is for X inside of Pn, there's a natural line bundle floating around, O1. So I can take its first term class. That gives me some cohomology class called H. It's an ample class on X. If you want to think about it in form language, this is represented by the Fubini study metric on projective space restricted. And I can cook up a form, right? I can declare Q alpha beta bar to be, well, do what I said. You wedge these two together. So I get something that's of degree 2k. So I need to bring it all the way up to 2n. So I just wedge with n minus k. This is now a top form. So I can integrate that, and this gives me a form. And I can write it in terms of cup product, so it's defined over Z. And it turns out that up to a very subtle sign, this will polarize the Hodge structure coming from what I said up there. Okay. So that's an important fact. Well, so don't forget it, but it's also, don't forget that you need to change the sign, but it's okay to forget how to say, I don't know. The important statement is that it's a polarizable structure. So up to fiddling around with this over Q, up to sign, that's important. That's, I don't know what to say. That's important, but whose details are unnecessary. That's, well, let me just say up to sign. This polarizes. So you don't see this in H1. Let me just briefly describe the kind of thing that can happen if you think about H2. Okay, so for 2 0 forms and 0 2 forms, there's no problem. This will have the correct sign. But if you look at type 1 1 forms, there's kind of two things that can happen. They can either look like a multiple of the Fubini study form itself, in which case you'll get one sign here, or they can look at something which is sort of perpendicular to this, in which case you'll get the other sign. Okay, so somehow you have to flip the sign depending on whether there's a multiple of H that shows up. So that's boils down to flipping the sign according to the Hart-Lefschetz theorem. So the Hart-Lefschetz theorem that describes how sort of the total cohomology breaks down when you include cupping by H as an operation. And on those pieces, this up to a sign is a polarization. Okay, questions about that? That's a bit technical, but like I said, the reason I formulated it this way is this kind of this is the takeaway statement. And those are sort of the details that, you know, in day-to-day life don't matter. Okay, great. So that.
So could you give an example of a non-polarizable?
That is a good question. I was in fact going to give that as an exercise, but we can also talk about it. But there are some other things I wanted to say, but let's talk about it at the end. Well, let me give it as an exercise. Exercise. Write down a non-polarizable, Z Hodge structure, Q Hodge structure even.
What goes wrong if you just like take something else in H2?
Sorry, say again?
Instead of your H, and you just take something else in H2, I mean, that's.
Wait, sorry, where are we and what is happening?
In Q on HK,
Oh, yes.
need some element, well, you need a 2 form, right?
Oh, you're saying what if you take some other thing and put it in here?
Yeah.
Well, it's gonna have to have some kind of positivity property, because that's what you're looking for.
Yeah.
And if you put, I mean, yeah. So, I mean, the fact that this is a Kähler form, meaning it has some positivity at every point, gets you some positivity out of this form. If you put something random, for instance, if it kind of switched side, if it was, it's not even clear if you took a random form, sort of how to relate the pointwise sign of this to the global sign of this integral. That's, this global thing is not clearly related. Does that make sense?
Yeah, my question is basically, is that somehow like the only choice?
Oh, you can pick any ample class
Yeah, okay.
and it will polarize.
So maybe it would.
You could even, there are even potentially some non-ample classes that you could take. In fact, you can look at the necessarily algebraic subset of H2 of cohomology classes that polarize the thing. And you'll get something. That's an interesting question, like what classes show up? Even the weaker condition that sort of Hart-Lefschetz is satisfied with respect to the cohomology class is kind of an interesting question. But I mean, this could be 0, right? If you took like a random thing, you could get 0 here.
Yeah.
Okay, that wouldn't be good.
I have another question.
Yeah.
Sorry, so you also want, okay, so the way I've written everything, this is in differential form, right?
Yes.
Now, you want, if you were to now look at elements in the Berry cohomology with Z values, you want the pairing to be an integer.
That's right, that's right.
Is that formal or is the content?
Well, it follows from the fact that under the integration comparison, wedge goes to cup product. Okay, so I can write this, you're absolutely right, and I kind of underhandedly said that in words, but I should have spent more time on it. This form, because I definitely do want it to be defined over Z, is defined over Z because it's cup product. And this H is also a Q class because that's the Chern class of the line. Okay, so in general, for a general Kähler manifold, for instance, You would have the same positivity for a Kähler form, but of course that may not be defined over Q, in which case you won't get a polarization for the Q Hodge structures. You would get like a polarization of the real Hodge.
Is polarizable open?
No. Exercise. So here's a simple way to, I mean, for a form Q to have any chance of being a polarization, the map you get from V to V dual had better be a morphism of Hodge structures. That's like Hodge-Riemann 1. Okay, so that already sort of picks out sort of a closed locus. And then on top of that, you have the Hodge-Riemann 2 relation, which is some positivity thing, so it's kind of an open sub of that. Yeah. Other questions? I think that's right? Did I say anything wrong? Yeah. Other questions? Okay, cool. Okay, so now I want to start talking about 2. Namely, I want to talk about parameter spaces of Hodge structures. So for this story, we want to fix a lattice and a quadratic form on it. And we want to understand the sort of space of all Hodge structures to put on that fixed lattice, which are polarized by that fixed form. Okay, so fix VZ, so that's some Z lattice and some form Q. And we also want to fix the kind of discrete invariance. So we want to fix the weight and the like dimensions of the VPQ pieces. So fix that, fix K the weight, and also what are called the Hodge numbers. Call them HPQ, but these are going to end up being the dimensions of VPQ, and they should satisfy a condition, namely HPQ equal to HQ. Okay, so what is the space of Hodge structures V on this fixed lattice with, dimension VPQ equal to HPQ and which are polarized by Q. And polarized by Q. Question. Okay, great. So you can think about this question and you would have some success, but you'll have much greater success with the following key observation. And this is the introduction of the Hodge filtration. Which is the filtration on the complex vector space. I'll call it VP FPB, but this is a filtration of VC, which just entails summing together all the pieces of the Hodge decomposition, where the first thing is bigger than or equal to P. Okay, so as P increases, this is a stronger condition, so this is a decreasing filtration. And why is this a relevant observation? Well, the point is, first of all, that the Hodge structure is determined by this filtration. That's for a very simple reason. I can recover VPQ by intersecting FPV and FQV bar. Okay, so that's important observation number 1. Important observation number 2 is that there's a simple condition for when a Hodge, so in the reverse direction, there's a simple condition for when a Hodge filtration comes from a Hodge structure. So filtration comes from a Hodge structure V, if and only if Well, some of the VPQs need to be this intersection. So if I shrink this by one step, there should be no intersection, and that's actually a sufficient condition. So if and only if, when I intersect FPV with FQ, but I want to make it one smaller, so that's increasing the degree, is 0 for all P plus Q equal to K. Okay, so this is a sufficient condition for a filtration to come along structure. And C, so this is just about the Hodge structure. It's not about the polarization, but the polarization sort of also nicely manifests in terms of this filtration. So I'll just say for Hodge Riemann 1, so remember Hodge Riemann 1, which I probably erased, says something about the orthogonality of the VPQ decomposition if I make the form Hermitian. And that translates into the filtration being isotropic for Q, meaning that if I take the perp of FPV, then it should equal FQ plus 1P, again, for P plus Q equal to K. Okay. So why is that good news? Should have just enough time to write this diagram. I meant to do some concrete examples, but I guess we'll start next time with that. Maybe we've been sort of carrying the elliptic curve with us, but I want to do some non-classical examples. But let me just come to the punchline here. The point of this key observation is that spaces of filtrations on a fixed vector space we understand. That's some algebraic variety. Right, so I'll call it D check. This is the flag variety of Q isotropic filtrations on VC, right? So there's a fixed VZ, and so there's a fixed vector space, VC, complex vector space, and I can look at all filtrations, which are Q isotropic in this sense. That's some algebraic variety. In fact, we can say more about it. Any two such filtrations can be moved one to the other via an automorphism of the sort of complexified lattice and form. So there's a transitive action of automorphisms of VC together with the form. And so this is just some homogeneous space for this complex algebraic group. This is automorphisms VC comma Q modulo some subgroup. What is that subgroup? Well, it's the stabilizer of a filtration, so it's some parabolic signal. Okay, so again, this is some concrete projective variety. Now, let's consider D, which is the set of Hodge structures of the correct type. Sorry, I should have said of the correct, with dim of Burr PFB equal to HPQ. Right, I want them to have the kind of right numerics. Okay, so now let's write D for the space of Hodge structures that we're after. Space of Hodge structures of the correct numerics polarized by Q. Before saying anything, this was just somehow some set. But part A tells you that this is a subset of D check, right? Because the filtration determines the Hodge structure. This is from A. And also from C, right? Because we needed to know that the Hodge filtration you get is an isotropic filtration. Now, if you look at the other two conditions, this one, which is some intersection being 0 condition, in particular, it's a generic condition. And the second one, which I didn't write down, which is some positivity condition, which is therefore also open. This is an open embedding. Yes, this is open by B, like C part 2, I guess. Let me call it. Okay, so this is an important observation because a priori this had no structure. But when we use kind of the Hodge filtration as the coordinates for the Hodge structure, we realize that we get an open subset of a projective variety. So in particular, this has the structure of a complex manifold, which is, completely not obvious just from the definition of a Hodge structure. I mean, not obvious without some additional thought. Even better, by kind of similar chain of reasoning, any two such Hodge structures can be moved one to the other by the real points of this group. And so that realizes D as a quotient of this real algebraic group by the stabilizer of a point. Call it M. But now, if you think about it, if M is a real automorphism which preserves Q, and Q is a polarization of the Hodge structure, well, then it also preserves this Hermitian form I built out of Q. So in particular, it preserves a definite form, and so this M is compact. Sorry, I'm brushing my things, but I want to get to a certain punchline. So that has the nice consequence, and this is sort of where we'll pick up next time, that if I look at the space I'm actually interested in, which is Hodge structures on the fixed lattice up to integral automorphisms, that's this space. Well, this is just this space, modulo on the left by a discrete subgroup. So it's just the integral point from this real group, modulo compact group. So this is a reasonable manifold, which in addition has the structure of a complex. And just very quickly, let me spend 30 seconds connecting this picture to the picture you probably already know, which is Hodge structures on an elliptic curve. So what is all the data involved here? Well, the underlying lattice is just a copy of Z squared. The form is just sort of the standard antisymmetric form. The Hodge numbers are, the 1, 0 and 0, 1 dimensions should be 1. What is D check? It's the space of isotropic filtrations, but for a line, isotropicity under an antisymmetric form is automatic. So this is just the projectivization of the complexified vector space. So this is a copy of P1, and it has a transitive action by automorphisms of the vector space together with the form, i.e. SL2C. And this is realized as the quotient SL2C modulo the upper triangular parabolic. And inside of there, we can look at the filtrations which give you Hodge structures which are polarized by Q. We know what that is. That's the upper half plane. It has a transitive action by SL2R. And it is identified with SL2R modulo the stabilizer point, which is compact. Which is one. And the resulting moduli space of Hodge structures of this type, which is what we actually care about, just this, which we know and love to be the modular curve, which is a well-behaved, a reasonable complex manifold. Okay, so said this way, it's not surprising that that story will sort of generalize to the general case, and indeed it will. So that's where we will pick up next time.
Any questions for Ben? Just about this last thing. First of all, here the weight is 1, right?
Yes, yeah, sorry.
And and just I don't see something. If the line you pick in VC squared is self-conjugate, then it's not gonna get you a Hodge decomposition, right? So it's every line, or you write that D check is.
Well, this is just about isotropic filtration. So real lines will still give you isotropic filtrations because the isotropicity condition is trivial.
Oh, okay, but you.
But it
don't-
doesn't give you a Hodge structure because this is some open sub. And the locus you're talking about is exactly the real line sort of at infinity for the hierarchy. And then the kind of other, the lower half plane is sort of the same thing, but you have the opposite sign condition.
Can you say something about why the filtration helps you build the moduli space? Why can't you just do it without the filtration directly in terms of the substantive?
Sorry, say again?
If you just tried building the moduli space directly from
Yes.
that definition instead of using the filtration, why would it be more difficult or why is it easier?
Well, your journey might be different, but for me, the complex conjugation gets extremely confusing to think about if you try to parameterize this, the decompositions into VPQ. I mean, decomposing into VPQ isn't so bad, but the conjugate symmetry makes things very complicated. Whereas this description, I mean, somehow, I mean, there are other things that are easier to see from that perspective, but the main things I wanted to read off from this description, for which the filtration actually helps, is the fact that it's a complex manifold. And that's actually going to be super important because we want to talk about families of Hodge structures coming from algebraic varieties. They should be holomorphic families in some sense. What does that even mean? Well, we have equipped this with a complex manifold structure, so now it will make sense. And if we unpack everything, what that means is you should be looking at the sort of coordinates of the Hodge filtration and how it varies, and those will vary holomorphically.
So just a follow-up question. How do we encode the conjugation into the filtration structure?
Well, sorry, I start with a fixed lattice,
Uh-huh.
which is a Z lattice, so it has a complex conjugation.
Uh-huh.
So I think that is the answer to your question. So it has to be compatible with the filtration, and
I
I mean, the filtration has to satisfy some conditions with respect to it in order to actually give you a Hodge structure.
I guess what you're saying is that this B condition is easier to write in terms of the filtration, the fact that.
Yes, absolutely, yeah. And indeed, I encourage you to actually work this example out in that language. And you'll see that the polarization condition, the positivity condition exactly cuts you out imaginary part of y bigger than z with the correct sign.
If I could just add one quick thing, there's a thing like, yeah, you want families of Hodge structures. You want things to be holomorphic. The VPQs can't possibly vary holomorphically because they're complex conjugate to each other. And so you make this FP object and that now can vary holomorphically.
Really naive. So if I just give you one Hodge structure that's polarized of pure weight K, is it the homology of a?
Excellent question. So the answer is no. And this is related to another thing that is only comes into focus when we introduce this Hodge filtration, which is the condition of Griffith's transversality. So when you have a family of Hodge structures coming from geometry, not only does this filtration vary holomorphically, but it varies in a certain way. And whenever that condition is non-trivial, it means that the image of a period map inside of these spaces can't be everything, can't be dominant. So it can only cut out subs, and now there are only countably many families of algebraic varieties, so you can only get countably many subs of a space for which that's a non-trivial condition, and therefore most Hodge structures of type where that is a non-trivial condition don't come from geometry. And which are the Hodge structures that, for which Griffith's transversality is automatically satisfied? Those are the Schmork varieties. So those are the cases when you can realize all the Hodge structures is coming from geometry. Well, ought to be able to.
As you brought that up, then so now if I take a variation and it has Griffith's transversality, the days come from geometry.
That is certainly not known, but it is at least conjectured. Could be appropriately with appropriate modifications, but it could be the case. That's like some kind of, some super strengthening of the Hodge conjecture. Somehow every polarizable integral variation of Hodge structure should in some sense come from geometry. And again, I don't know whether you should believe that, but that's at least a statement that could potentially be true.
Wait, maybe this is stupid, but what stops you from taking something that does satisfy Griffith's transversality times like a constant Hodge structure that doesn't come from geometry or something like this?
Yeah, so that's the part I said ... over. That's that part. yeah, you want to, I mean, you could take some variation, you could just kind of tensor by something, some generic thing which doesn't come from geometry, then there's no reason for that.
Okay.
You want some kind of irreducibility hypothesis on the monodromy or some kind of condition to rule it out, but that should basically, I mean, that should basically be the only obstruction to, you know, at least conjecturing that that is true.